So I just want to remind you that if you wrote this down in 6th grade, that was really exotic. That was somebody telling you that there was a special notation we defined for what it meant to multiply two numbers together. And then you said, well, if we do this, we can mean a times a times a, and in general, a to the n just looks like a times a with n copies. In this setting, n has to be a counting number. And then, of course, in hindsight, it makes sense to call a to the first power as just one copy of a. But it's a little bit unclear what even a to the 0 power should be, or even if you could make any sense of it. And so you go through and you say, well, let's figure out, once we've developed a notation for something, we want to figure out how it behaves. And so we go through and we say, well, if we take a squared times a to the third, well, that's just shorthand for a times a times a times a times a, right? We have a group of 2 things and a group of 3 things, giving me a total of 2 plus 3, which is 5 things. And we say, wow, that works really well for whole numbers. Well, what we're going to insist is that we don't have different rules for different kinds of numbers. We get a rule coming out of this. For all x and y, we're going to insist that a to the x times a to the y is a to the x plus y power. Not just for whole numbers, but the rule for whole numbers is what we're going to mean for all numbers. You similarly have, if you take a squared and cube it, that's a times a, one group of 2, a times a, right? We take the number, how many copies are there? Well, there's a group of 2, another group of 2, another group of 2. So this is 3 groups of 2, and so what we're going to get is a to the 2 times 3, in other words, a to the 6. You have a group of 3, another group of 3, and so what you have is, instead of 3 groups of 2, you have 2 groups of 3, and so what you get is a to the 3 times 2, which is also a to the 6, and so you get another rule. A to the x to the y is equal to a to the xy power. Now, those are actually the only 2 rules of exponents that we ever use. All the other rules you might have learned for exponents are defined, are consequences of these 2. So for instance, how do we get to other kinds of numbers for powers? For instance, if we look at a to the 0, I want to know how that should be defined. Well, everybody knows it's got to be 1, but how many people can explain why any number to the 0 power is 1? And why do so many of my students seem to think that any number to the 0 power is 0? Because it was an arbitrary fact they memorized. Nobody ever told them why, and so it's Teflon knowledge. You turn your head sideways, it falls out your ear. We don't want that, right? So what we know is that if we take a to the 0 times a to the first, we have a rule that says that has got to give me 0 plus 1. In other words, whatever a to the 0 is, if I multiply it by a, I get a. Now, if I've written that down first, what has to go in the box? 1. A to the 0 is equal to 1. That's another rule. For any base a, other than the number 0, 0 to the 0 is undefined. It makes no sense to talk about it. Not because somebody arbitrarily defined it, but because if the rules for exponents are going to work, it has to be 1. No choice. Similarly, if we look at a to the minus n, where n is any power, well, I know that if I multiply that by a to the n, I get a to the minus n plus n, which is a to the 0, which we newly discovered is equal to 1. So if we think about what has to go in that box when it multiplies by a to the n to give me 1, that tells me the thing in the box has to be 1 over a to the n. In other words, a to the negative of a power is 1 over a to that power. Not because somebody declared it, but because you have no choice. It has to be that way based on those two basic rules. What about if we wanted to do this, like the 1/3 power, the 1/5 power? I get a lot of students who think I'm just multiplying by the power. It'd be a over n or something. I mean, just because it's just muddled. But if I look at this and say, well, our second rule, this is the first time we've used the second of our basic rules, by the way. If I multiply the exponents, 1 over n times n, that's equal to a to the 1, which is just a. So this thing has the property that when I raise it to the nth power, I get a. And that tells me the thing in the box is equal to the nth root of a. So if I take the 1/3 power, that's the cube root. The 1/2 power has to be the square root. Because when you square the 1/2 power, you get the number back. When you cube the 1/3 power, you get the number back. So what we have is that any number to the 1 over n power is just the nth root of that number. That allows us to compute any fractional power. For instance, if I take 7 to the 3/8 power, I can think of that as 7 cubed to the 1/8 power. That's the 8th root of 7 to the 3rd. Or I could think of that as 7 to the 1/8 cubed, and so that's the 8th root of 7 quantity cubed.